Hi, and welcome to Culligan International, the world's leader for solutions to water quality problems. We're going to talk about some of the methods available to us for treating these problems. But first you might ask, how does water become contaminated? Water has been called the universal solvent. In fact, water likes to dissolve most anything it comes in contact with. When in the atmosphere, water is exposed to a host of contaminants, such as carbon dioxide. Carbon dioxide and water form carbonic acid. It is possible that water could also be exposed to nitrous oxides and sulfur compounds from the burning of fossil fuels. You might have heard the term acid rain. This is primarily how it is formed. As water falls in the form of precipitation, the carbonic acid in the water will begin to dissolve elements in the Earth's crust. Sediment layers such as limestone are the major contributors to the hardness minerals calcium and magnesium, which are found in water supplies. Now that we've determined how substances get into the water, it's important to be able to identify them so that we can design the proper equipment for the application. The device to my left is an atomic absorption spectrophotometer. It is utilized to identify the cationic substances in the water, primarily calcium, sodium, iron, and nickel. The atomic absorption spectrophotometer draws in a small sample of the water and delivers it to the flame. Notice how the flame changes color as the water sample is delivered to the flame. This is because each element has a characteristic spectrum. The cell to the left of the flame monitors the intensity of the wavelength of that spectrum. The intensity allows us to determine how much quantity of that substance is in the water. The results are recorded in the computer, and the computer will then print out a report which will be delivered to the customer. Another method to identify the substances in the water is to do a wet chemical titration, similar to what is done in chemistry laboratories. Each drop represents 1 grain of hardness in the water. As soon as the pink solution turns blue, we have reached the end point of our titration. This represents about 18 grains of hardness for our water supply. 1 grain of hardness is equivalent to 1/7,000th of a pound. Now this might not seem like a lot, but the average home uses 300 gallons of water per day. If we had a 10 grain per gallon water supply, this amount of hardness would be represented in only 50 gallons of water. So you can imagine how much hardness solution or hardness minerals are passing through the pipes of an average house per day. You might ask, why does any home need a water softener? Well, hard water consumes more energy in hot water heaters and also requires you to use more soap. I have a standard soap solution, and I'm putting 3 drops in soft water and 3 drops in hard water. As we shake these, you'll notice soft water produces a lot of sudsing action. The hard water produces no suds at all. So we can see that soft water allows us to use soaps more efficiently, but also in industry there are problems with clogging of boilers, cooling towers, and other heating elements which could rob and cost industry a lot of money. Hard water will scale pipes, and also it will reduce the efficiency of water heaters and other water-using appliances. As water is heated, such as in a water heater, the calcium will combine with the naturally occurring bicarbonates to form calcium carbonates. This is the hardness scale. The calcium carbonate will deposit on the inside of pipes, slowly narrowing them. You can also plug up the pipes and also plug other water-consuming devices. A water softener uses a special media, commonly referred to as a resin. The resin is specifically formulated to have negative exchange sites. These negative exchange sites attract the positive cationic metals in the water. A water softener consists of 3 components: a control valve, which is the brains of the unit, a resin tank, which holds the media, which we saw previously, and a salt storage container. The ion exchange process takes place in the media tank. As the water passes through the ion exchange resin, The dissolved metals in the water, the calcium, magnesium, iron, and other dissolved metals, will be exchanged onto the resin for the sodium ion. The softened water then travels to the bottom of the unit and exits the outlet manifold into the home. After the water softening resin is exhausted, the regeneration process will take place. The control valve draws the brine solution from the salt storage container over the water softening resin. The brine is saturated with sodium ions and chloride ions. The sodium exchanges back onto the resin, forcing the calcium and magnesium and other soluble metals off the resin and out the drain. You might wonder why a water softener doesn't cause the water to taste salty, especially since it's using a brine solution during the regeneration process. That's because the chlorides are an anion, and anions have negative charges. The resin in the water softener is only attracted to positive ions. Therefore, the negatively charged chlorides are flushed to the drain with the other hardness minerals. Whereas a water softener will only exchange one ion for another process, reverse osmosis, will actually reduce the dissolved solids content of the water. The process begins with the membrane. This membrane is a spiral wound membrane and is the most popular used in the industry today. In order to understand the reverse osmosis process, we first must understand osmosis. Osmosis occurs naturally every day in nature. It's how our bodies get nutrients. It's how trees and plants get water. Basically what happens is water will travel across a semi-permeable membrane to a more concentrated solution in the attempt to dilute that solution to become at equilibrium with the less soluble solution. In a reverse osmosis process, we reverse this procedure. We apply pressure to the concentrated solution, forcing water through the membrane, leaving the impurities in the concentrate solution and allowing only pure water to pass through the membrane. The reverse osmosis membranes are first manufactured in sheets. Each sheet has a membrane that is about 10 feet long, approximately 12 inches wide. The sheet is then wound on a center tube, hence the name spiral wound membrane. We've only focused on 2 technologies to treat water. There are a whole host of others available, such as deionization and ultraviolet. In fact, as long as there are contaminants in the water which need to be removed, we are always going to be faced with the challenges to find economical solutions to these problems.